Hi, folks. This is Bob Cunningham, and I'll be sharing with you today a bit about numbering systems we use in networking. So let's start with how gigantically big the internet is. There are over 22 billion computers, 4 billion plus users. This is a graphic designed to show this to you. Um, just imagine every one of those points of light is a network, usually, not even just a computer, a network. Huge. We have to have a way to keep track of all this. We do it with numbering systems. Now, these computers are made up of billions of switches. So this is a symbol of a transistor. Don't worry about what that is, except that if you know what a transistor is, you'll recognize that. What a transistor is basically is an electronic switch. It has two states, on and off. As it turns out, there's a numbering system that does a really good job of representing on and off. It's called binary. And that's what we're going to look at first. How does binary work? Well, as I mentioned, a typical laptop, maybe 3 billion of these switches. And we can use those switches to represent music, videos, run programs. But no matter how complex the image, how complex the program, how interesting the music, it's still a series of ones and zeros, a series of switches that are on or off. Now, to understand binary well, it's going to help you to remember what you learned in school about decimal. So this is the decimal number 436, but it's really more complicated than that. Here in the, we could call this the ones column, call this the tens column, call this the hundreds column. So what we're really saying here is that we have 6 ones. So I've got these blocks here, right? 6 little blocks. 1, 2, 3, 4, 5, 6. 6 ones. Now for the tens, I'm going to use a group of blocks, a group of 10 blocks. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks here. I've got 3 groups of 10. And that's what we mean. We put a 3 in the tens column, 3 groups of 10. Now, in the hundreds column, these are 10, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 by 10 is 100. Each of these squares is 100 of these blocks. So we've got 1, 2, 3, 4 of these hundreds. So really, when we say 436, we're saying we've got 4 hundreds, 3 tens, 6 ones. Kind of keep that in mind as we look at binary. Binary doesn't have a ones column and a tens column. Because we're just dealing with states of ones and zeros, every column is double the one before it. So we have a ones column. The next column over is not a tens column, it's a twos column. After that is a fours column. After that's an eights column. So if I have a 4-bit binary word, by the way, that's referred to as a nibble. I have a 4-bit binary word here, and 0, 0, 0, 0, all zeros. Guess what that's equal to? You guessed it, 0. Now, what if I put a 1 in the ones column? Well, then I have no 8s, no 4s, no 2s. I have a 1. That's going to be equal to 1. Well, the next column over is the twos column. That's probably pretty easy, right? No 8s, no 4s, a single 1 and a 0. It's going to equal 1 in the twos column. All the rest is zeros, equals 1. 2 rather, excuse me, equals 2. Now, there's no 3s column. But if I were to take and add 2 and 1, that would give me 3. So a 1 in the ones column, a 1 in the twos column, the total there is 3. To get to 4, there is a fours column, so we put a 1 in the fours column, 0 everywhere else, 0 here, 0 here, 0, but a 1 in the fours column will give us a value of 4. Well, 5 is 4 plus 1. Put a 1 in the fours column, a 1 in the ones column, we have a total of 5. 6 can be made up of a 2 and a 4. 4 plus 2 is 6. So I put a 1 in the fours column, a 1 in the twos column, and I get 6. 7 is a 4 and a 2 for 6, and one more is 7. The next one up is the eighths column. So I just put a 1 in that column, 0 in the rest of the columns. That gives me an 8. 9 would be an 8 and a 1, gives me a 9. 10 is an 8 and a 2, gives me 10. 11 is 8 and 2 and 1. And then, of course, 12 is 8 and 4 to give me 12. 13 is 8 and 4 is 12, plus 1 is 13. 14 is 8 and 2, 8 and 4 rather, for 12, plus 2 is 14. And then 8 and 4 and 2 and 1 would give me a total of 15. And that's how we would count to 15 in binary. The only difference between that and decimal is where each column has a different weight. Instead of ones and tens and hundreds and thousands, it's ones and twos and fours and eights. And again, the reason we do that is because inside of our computers, it's just a series of ones and zeros, of switches that are on and off. Now then, how would you go from a decimal number? So there we've taken and sort of stepped you through a nibble, all the 16 possible values from 0, 0, 0, 0, all the way up to 1, 1, 1, 1. And by the way, if this is not sticking with you, go ahead and rewind this and watch that progress of 0, 0, 0, 0, all the way up to 1, 1, 1, 1 over again. And if you have to look at it several times, that's fine. How would I go from a decimal number into binary? Let's say I have the number 13. I'd like to know how to express 13 in binary. So let's move 13 out of the way so we can get some space to write in. And I'm going to start writing out columns. You recall my first column was 1, so I'll put a ones column here. Next column over is 2. Next column over is 4. I'm not doing anything except writing the columns out right now. 1 and 2 and 4. The next column up is 8. The one after that, if we were to write it, we can continue going up. The one after that would be 16. That's bigger than the number I want, so I stop there. I don't need to go that high. So I've got the number 13. Let me go ahead and subtract and see, can I subtract 8 from 13? Well, yes, I can. Gives me a result of 5, right? I put 1 in the eighths column. Now I'm going to ask myself, can I subtract 4 from 5? Because I subtracted 8 from 13, I got 5. Now can I go 4 from 5? Yes, I can. And I have a remainder of 1. Can I subtract 2 from 1? No, I can't. So I put a 0 in that column. Now, I still have that remainder of 1. Can I subtract 1 from 1? Yes, I can. So the 13 is a 1 in the ones column, a 0 in the twos column, a 1 in the fours column, a 1 in the eighths column. That will give you a total value of 13. You can convert any number to binary that way. Supposing I had, I don't know, 152. I'd write out the ones column, the twos column, the fours column, the eighths column, the 16s column, each one double the one before, 32, 64, 128. The next one over would be 256. That's bigger than my number, so I stop there. Let's take 152 here. Subtract 128. Put a 1 in the 128th column. Now, that's going to be a remainder of 24. And can I subtract 64 from 24? I can't. A 0. 32 from 24? No, a 0. 16 from 24. I can do that. Gives me an 8. 1 in the 16th column. 8 from 8? Yes. Gives me a 1 in the 8th column. 4 so subtract 8 gives me 0. 4 from 0? No. 2 from 0? No. 1 from 0? No. That's all there is to it. Now, for this course, all I want you to have is an understanding of how this works. You can go online and just type in binary calculator, and you get a piece of software that will convert binary to decimal and decimal to binary. but I want you to have a sense of when we talk about a binary number, where it came from. Not the exact value. I don't care if you look at this number here. And I don't care if you can tell me what that is in decimal, but I do want you to know, A, it can be represented in decimal, and B, it's logical how we get to the decimal number. All right, if you can do that, then we're good up to this point. And we're converting binary to decimal. So I've got this just one more time. I've got a ones column. I've got nothing in the twos column, a fours column, and eights column. So it's 1, 4, and 8, 13, right? So add the 8 and the 4 for 12, add one more for 13. Now, terms that you may not be familiar with. A single binary digit is called a bit. In fact, the word bit is the contraction of binary digit or bit. 8 bits make up a byte. So this would be an example of a byte. 8 binary digits is a byte. It is frequently useful in networking and in programming to represent 4 bits by themselves. So we have a way of referring to, if this is a byte, this is a nibble. So you should know, and if you don't know, you should memorize the terms bits, bytes, and nibbles. There is a special numbering system because we use nibbles all the time. There is a special numbering system that will allow us to represent a single nibble as one character. In other words, you know from what we just looked at that 4 bits can go from 0 all the way up to 15. Of course, 15 is 2 characters, as is 10, 11, 12, 13, and 14. Hexadecimal lets us take and do that with 1 character. So if you have a nibble of 4 binary bits, in hexadecimal, 0 through 8 look like 0 through 8. So we have the binary over here, and just 0, 1, 2, 3, 4, 5, 6, 7, 8. 9 looks the same as it does in decimal. But now we have 10. 10 has 2 characters normally, 1, 0, right? That's how we used to seeing 10. In hexadecimal, we will represent a 10 as the letter A. And we do that so we can have one symbol, a single symbol representing all 4 bits. So for the value of 11, we'll represent a B. 12, well, that's a 4 and a 1 in the 4's column, a 1 in the 8's column. 12 would be the letter C. 13 is a 1 in the 1's column, 1 in the 4's column, 1 in the 2's column. D. 15, or 14 rather, will be a 1, an 8, a 4, and a 2, the letter E, and then all ones, an 8, a 4, a 2, and a 1, will be the letter F. This is just something you kind of need to memorize. The ABC, it makes sense if you understand binary, that this nibble needs to have 1 character, and we use it all the time in networking. This will, if you go to work in networking, you'll be using this notation all the time. So do get used to the idea that an A equals a 10. You don't have to remember the binary piece of it, but you do need to remember A is 10, B is 11, all the way up to F being 15. So here's an example. I've taken 16 bits, 2 bytes. I've broken them out into 4 nibbles. Each nibble is 4 ones, so I can represent these 4 nibbles as FF, FF, and it's the same thing as having written out 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. All ones for 16 bits. If I was to change one of the middle nibbles, the second nibble this direction, okay, from a value of 15 to a value of 1, that would still, this would be F, 1, F, which is what you see right here. If I was to change this into a value of 14 instead of 15, this would be F for a value of 15, F for a value of 15, 1 for a value of 1 of the ones column, no zeros, and then 8 and 4 and 2 gives me 14, which is a hexadecimal E, which is what you have here, FF1E. We'll be coming across this when we talk about something called a MAC address. We talk about something called IP version 6. So this is coming in the future. You'll need to know this. This is sort of foundational, which is why this is being presented before your normal coursework. Now, again, as a review, a bit is a single digit. A byte is 8 bits. A nibble is 4 bits. There are addresses, in particular IP addresses, IP version 4 addresses, that are made up of 32 bits. In order to more easily represent that, we take the 32 bits. So this is 8 bits, another 8 bits, another 8 bits, and a final 8 bits. We take each of those 8 bits and we convert them into decimal. And we put a dot between them to remind us that each of those numbers is a separate representation of a separate 8-bit word. So 7.17.15.3 means this 8-bit word has a value of 7. One of the ones column, one of the twos column, one of the threes column, fours column rather, nothing else. Total of 4 plus 2 plus 1, 7. 17, a 1 of the ones column, no 2, no 4, no 8, a 16. 16 and 1 is 17. 15, a 1, a 2, a 4, and an 8. Add them all together and you get 15. 3, all zeros, but a 1 in the ones column, a 1 in the twos column for a value of 3. That's called dotted decimal, and you will use that every day of your life if you work in networking. You'll also need to get used to the metric names for groups of numbers. In English, we say, "Oh, 1,000. I have $1,000. I have 1,000 pounds. I have 1,000 cucumbers," whatever. In metric, it's kilo. In English, I hope to have $1 million. In metric, it's mega. Billion is giga. Trillion is tera. So you'll need to get used to the terms kilo, mega, giga, and tera, because once again, if you work in networking, you'll come across these terms all the time, and it will be assumed that you understand the value of the magnitude we're talking about. On the smaller side, 1,000th we call a milli. So when we're talking about drugs or chemicals, and I will say a milligram, a milli. 1 millionth is a micro. 1 billionth is a nano. 1 trillionth is a pico. These values here are used frequently if you're dealing with optical signals. There's something in optics called wavelength versus frequency, and they're the inverse of each other. Those are a really big frequency is a really small wavelength, and a really big wavelength is a really small frequency. The last thing, and then we're done with this introduction. Networks are made up of 4 pieces, and you'll need to know what these 4 pieces do. So at the simplest level, you have a computer. The computer is the source or the destination of the information. So here's a computer, and maybe it's talking to this computer over here. Then you have a device called a switch that creates a network. So all these devices here, all these computers are on the same network because they're attached to the same switch. Over here is a different network with different computers attached to a wireless access point, which is a wireless switch. We have a transmission media or a method. Here we're using radio waves. Here we're using electrical wires. Somewhere else we're using optical cable, the physical transmission media or method. And then finally, routers connect different networks. So here's a network over here, call it network 2, call this network 1. They can't talk directly to each other unless they go through a router. Routers connect networks. Switches create the networks. Routers connect the networks. So to start with, I'd like you to have the simple definitions. The networks are made up of computers that are the source and destination of the information, switches that create networks, transmission media, where the ones and zeros move across, and routers that connect different networks. So before we start our journey together, you should understand what is binary, have a basic idea of how to convert a binary from a number, from decimal to binary up to 15, and from binary to decimal from 0, 0, 0, 0 up to 1, 1, 1, 1. What is hexadecimal? How hexadecimal symbols represent numbers from 0 to 15, and how you would convert, it says up to FF, just F. Convert a hexadecimal number to binary from 0 to F, what that would be in decimal. Understand the concept of bits and bytes and nibbles. Understand the measurement units of kilo and mega and giga and tera, and the units of milli, micro, nano, and pico. Know that hosts are the source and destination of data. Switches create networks, and routers connect different networks. If you don't understand that, get yourself some 3x5 cards and just write this stuff out. Some of this just be rote memory, just having their just flashcards and say, okay, bit, 1 single digit, binary digit, byte, 8 bits, just like that, until you've got this stuff down, and this should be mastered by you before we start our first lesson together. I look forward to our time together, and this is going to be an exciting adventure for all of us.